Okay, last time we did surface area, lateral, and total surface area of prisms and cylinders. Today we're going to do the same thing for pyramids and cones. So, same type of story. Alright, the vertex of a pyramid is the point opposite the base of the pyramid. The base of a regular pyramid is a regular polygon. So that phrase regular is coming back from chapter 4 even. Regular means equilateral and equiangular. Sorry, my strap keeps falling. Alright, and the lateral faces are congruent isosceles triangles. So if all of the bases are the same, then that's going to make all of the faces around the side going to be the same as what that says. The slant height of a regular pyramid is the distance from the vertex to the midpoint of the base. So slant height goes from the top and it goes down the middle of any face you want to, down to the midpoint of the base. So straight down the side. Not an edge like this, but a slant height goes down the middle of the face like that. The altitude of a pyramid is the perpendicular segment from the vertex to the plane. So the altitude in a regular pyramid, which is what we're going to study, not a non-regular, but a regular, is going to go straight down the middle and it's going to connect in the center like this. This is going to be your altitude. Okay, so here's a non-regular pyramid. We don't really study those this year. You might later, but for our purposes, we're going to do a regular pyramid. So slant height down the middle and then altitude down the center there. Okay, formulas. The lateral and total surface area of a regular pyramid is 1/2 PL, where P stands for perimeter of the base, and this cursive L, so you can tell it's not a 1, it's cursive, stands for slant height. So remember slant height from the vertex to the middle of the other side. Total, you're going to keep your lateral and then you're going to add the base on there. So the big B, we still have our 1/2 PL for the lateral, and then the big B, remember, stands for area of the base. So that's going to change depending on if you have a triangular pyramid or a hexagonal pyramid. It just is going to change. Alright, so let's do one together. Alright, find the lateral and surface area of a regular square pyramid with a base edge of 14 and a slant height of 25. So let's start with lateral. 1/2 PL. So if this is a square and the edges are 14, then the perimeter would be 56 and the slant height is 25. So it's just a matter of plugging into a formula at this point, and we get 700 centimeters squared. Then for total, we're going to keep that lateral, so we're going to keep that 700, and we're going to add on the area of a base. So since this is a square base, 14 by 14, 700 plus 14 times 14 is 896 centimeters squared. Remember, your total surface area should always be more than your lateral, so if you get something smaller, that's a way to check yourself to say, whoa, I did something wrong. Okay, try part B yourself. B is a hexagonal pyramid, but remember it's regular, so that brings back regular figures from chapter 9. So 1/2 PL, the perimeter is 60 and the slant height is 16, so that's 480 inches squared. And for the total, we keep our 480 and we're going to do our 1/2 AP. So since this is a hexagon, remember we can use our shortcut. The apothegm is half on the square root of 3, 5 on the square root of 3. Solve that out. You have your 480 plus your 150 on the square root of 3. So just because we're out of chapter 9 doesn't mean we lose our areas of hexagons. They're going to keep coming up all this chapter too. Okay, let's move on to cones. Cones are similar to pyramids. You still have your vertex, which is your point at the top, opposite of the base. You have an axis, which is like your altitude if it's a regular cone. It's going to connect the base to the point, to the vertex. And the axis of a right cone, this is what we were just talking about, is perpendicular to the base. So that is going to be your altitude. If it's an oblique cone, remember that phrase oblique from last lesson, meaning tilted, then it's not going to be perpendicular. Here's your pictures for that. They ended on the other page. So this is the right cone. This is the one we're going to work with the most. So your axis, you see it going from your vertex down to the middle, and it's perpendicular. So that is going to be our altitude, our regular height that we will need to use for volume in a few days. We still have a slant height, which is going from the vertex to the outside. So let's look at this. If this is a right angle and this is your slant height, look what you formed here. Now this isn't perfect. It isn't perfect drawing because it's 2D, but you can see that you formed a right triangle here between your slant height, your altitude, and your radius here, and that's going to come in handy in a little bit, knowing that this is a right triangle. Okay, here's a picture of an oblique cone. We don't really do oblique cones, but just so you know the difference here. Oh, this is what I was just talking about. The slant height of a right cone is the distance from the vertex to the point on the edge, and the altitude is the distance from the vertex straight down to the center. So the slant height will always be bigger than your altitude. Okay, here are our formulas for lateral surface area. We have pi RL. So that's, remember L, the cursive L stands for slant height. And then for total, same story, we're going to keep our lateral and add on the base. Now, instead of having to keep this big B, since this is a cone, the only base I'm allowed to have would be a circle. So I can go ahead and input that pi r squared in there to help me so I don't have to worry about what the base is. I know it's going to be a circle all the time. Okay, here we go. Find the lateral and surface area of a right cone with a radius of 9 and a slant height of 5. So lateral, pi RL, radius of 9 and a slant height of 5, so 45 pi centimeters squared. For total surface area, we're going to keep our lateral and add our pi r squared. So keep our 45 pi and add pi times 9 squared. So we have 45 pi. Sorry, my camera died. So we have 45 pi plus 81 pi, and that's going to give us our 126 pi. Okay, so go ahead and try B by yourself. Okay, so for this one, they gave us the altitude, the vertical height. So we have to do Pythagorean theorem to find the slant height. Now, luckily, this one was a Pythagorean triple, 8, 15, 17. So it came out nice and pretty, but it might not come out pretty. You might have radicals in there, and that's okay too. So pi RL would be 136 pi. We keep the 136 pi, and we add our pi r squared, so 64 pi, resulting in 200 pi. Okay, now we're going to keep doing our what if we change dimensions. So they say the base edge length and the slant height are divided by 5. So that means both dimensions, not one or the other, but both. So describe the effect on surface area. Now the long way to do this problem would be to find the surface area of this hexagonal pyramid. Divide both dimensions by 5, find the new surface area, and then compare it. But that's a lot of work for this one problem. Good thing we have our shortcuts. So we know our scale factor is to divide by 5. I'm doing surface area and I'm changing both dimensions, so I'm going to square that. So I'm going to divide by 25. So I will say the surface area will be divided by 25. Describe indicates a full sentence, so make sure you're doing that. Okay, try B by yourself. The base edge length and the slant height of a square pyramid are multiplied by 2/3. Same story, they change both dimensions, so 2/3 squared is 4/9. Alright, last one. The pattern shown is used to make a paper cup. What is the diameter of the cup? Alright, this is a couple step question here, and you really have to know how the net folds up to be the actual cone. So remember, we practiced this before spring break. We said when we fold this up, this curved edge is actually going to become the circumference of the cone, because that's how we're going to make our cone. It's going to roll up into a circle. And then this guy right here would be our slant height. It would be L. Now, however tall the slant height isn't necessarily telling us anything directly about the cone itself. So we're going to have to do this in 2 steps. So the first step we're going to do is we're going to look at this as it is a 2D figure right here. And I can tell that this figure is a semicircle. So I could pretend, okay, what if this were a whole circle and this were 8? Then I would know the circumference of this whole circle would be 8 pi, because I know the formula for circumference is pi d, pi times diameter. Well, I don't want to know the whole circle, I only want to know this side over here. So I can cut that in half, and I can figure out that this part right here is 4 pi. Then, now I can take it from this semicircle and I can pretend to roll it up in an actual net. So what we know is that this is going to roll up, and my cone right here is going to have a circumference of 4 pi. And we just talked about if circumference is pi times diameter, then looky there, my diameter must be 4. Okay, so let's talk through that one more time. So the first thing we did is we looked at this as a semicircle. We said if this is a semicircle with a diameter of 8, then the circumference of that whole circle, if I filled it in, would be 8 pi. But I only want half of it. So this curved edge that I'm given in this picture is 4 pi. Then we used what we know about our net, and we said, hey, when I roll this thing up, this curved part right here is going to become the circle of my cone. So I'm going to have 4 pi as the circumference. So then that means the diameter has to be 4. So it does just get cut in half from 8 to 4, but you really need to know why and the whole process behind the whole thing. So there you go.